Hello, my name is Rastgoo, and I'm from University Putra, Malaysia, and I'm here to talk about my FYP presentation on numerical investigations on laser transmission joining of dissimilar polymer metal materials. So to start off, I'm going to give a very quick background on my topic. History-wise, Einstein was actually the first person to suggest the fundamentals of lasers. However, since he was very much ahead of his time, it took more than 70 years until first experimental trials on laser joining began. When identifying laser joinings, they're actually under high energy beam welding, and they're usually used for high precision and small geometries and small parts production. The importance that they're facing nowadays is that, based on Dr. Hu-S-J back in 2014, nowadays it's generally not feasible to produce a product without some kind of integration, thus showcasing their significance and importance to the industry. And naturally, as it stands, many manufacturers look to use different materials to enhance their products using laser welding, because what's important for them is ensuring that products are manufactured of high quality as well as cost effective. With that said, we transpose into some of the problem statements. So Dr. Martinson et al. In 2015 said that due to some trends such as lightweighting, increased performance, and functionality, this has increased the use of multi-material structures and thus the need for joining dissimilar materials. So forth, Dr. Farazila in 2012 stated that traditionally metal and plastics are joined using mechanical or chemical joining methods such as fasteners or adhesives, but this was limited in terms of use since we couldn't use them to join small geometries, and hence we need to look for another method such as laser joining. Dr. Carlson in 2015 specified that while trial and error might be the simplest method to achieve solutions and or answers, they might take a huge amount of time and cost. So in order to decrease these two factors, we can look into numerical solutions. With that said, we now go into the three main objectives of this presentation. So first of all, we want to investigate the thermal distribution on laser joining by developing a finite element model. Then we characterize the effects of process parameters on laser joining of dissimilar materials, and we analyze the combination of various metals and plastics by means of laser joining. So this is the overall project flow chart of the entire project, consisting of two different finite element analysis stages, stage 1 and stage 2, which we're going to talk about specifically. So in the first one, to achieve the first objective, two materials were used. One was the ASI 304 stainless steel, and the polymer material was PMMA. So we're representing metal and polymer here as two very dissimilar materials. So to enhance the results, we actually use tabular data for specific heat capacity, density, and thermal conductivity, as shown in the graphs below. For the geometry modeling, first we had the initial experimental value, but in order to make the simulation much more simple, we transposed it into the final figure we see below, a 30/15 ratio. For the sensitivity analysis, we used a mesh number of 4,609, which was consisted of a fine mesh, because if the mesh was coarse, we would get inconsistent results. The heat input, the parameters we used were 4 millimeters per second for the velocity, a diameter of 1.5 millimeter for the beam's radius, and a power density of 21 watts per millimeter square. And the graph below shows the start and end points that were selected for the simulation. Two boundary conditions were used. One was the ambient temperature and the other one was heat convection. Naturally, the ambient temperature was room temperature 25 degrees Celsius or 297 kelvins, whichever one was suited best. Finally, we ended up with the first solution scheme for the first result. Based on the first figure, we can actually see the temperature contours for the finite elements analysis stage 1. What was important for us, we compared this to Dr. Hussein et al.'s work way back in 2017. So what was important for us was that the margin of error between the results that we got and Dr. Hussein et al. Had to be less than 15%, which is why the interface, lower surface, and upper surface results consisted of 12.1, 14.2 and 5.8% respectively, thus concluding that the method that we use, though might be different than Dr. Hussein et al., showed very similar results. And thus we transpose into the second finite element analysis, where we did process parameters and alternative materials. For the process parameters, we used in total 6 different cases, each of them focusing on 3 different parameters: one, scanning speed, power intensity, and beam diameter. For alternative materials, we had 4 different combinations. The first 2 combinations focused on substituting the metal material, while the third and fourth combination focused on substituting the polymer material, as you can see here. For cases 1 and 2, in the first process parameters results, we can actually see the results where decreasing the beam's velocity actually increased the thermal temperature, while increasing the speed actually decreases the thermal temperature, as expected. The results can be seen below. However, when we did this experiment with power intensity for cases 3 and 4, by increasing the power and intensity, we actually increased the thermal distribution, thus getting much more effect on the beam, increasing the maximum temperature, which could result in inconsistent joints. But the results can be seen here where we change the power intensity, we can significantly affect the final outcomes. For 5 and 6, where we change the beam's diameter, actually by shrinking it, we had less thermal distribution, and by enlarging the beam's diameter, we were able to mass produce the effect, thus having a much more effect on the thermal distribution and therefore enhancing it. These were the results we got for the parameters, and when we did it for different combinations, but with constant parameters, these are the results that we got. Naturally, they were different because these materials will have different absorptivity coefficients and different properties. Based on the graph here, we can actually see that each of them were different in their own respective way. The first two combinations, which were focused on changing the metal material, showed inconsistent results, while at the same time showing the graph shows that the experiments done for when we substituted the polymer material actually showed consistent results, thus showing a coherent joint. Now we can compose into the conclusion. For the first objective, with a margin of error of less than 15%, the project results were reasonably aligned with the experimental work done by Hossein et al. 2017. Thus, this confined the numerical method that we use, and we were able to use that justification to go for objectives 2 and 3. For objective 2, examination on the speed and thermal distribution showed an indirect lead. However, it showed a direct relationship between power intensity and heat distribution, as we showed. However, changes in the beam's diameter showed that by shrinking the diameter, we had less temperature distribution, and enlarging it, we would get a much bigger temperature distribution on the component, thus concluding the examination on the process parameters. Regarding objective 3, the first one concluded with PMMA and structural shit actually showed an incoherent joint. This was because the parameters selected were not suitable. Naturally, we have to find the best parameters using for this, but since we stuck with the same parameters which were used for PMMA and stainless steel, this showed that the parameters do not match when we change the metal material. Similarly, so when we did this experiment with aluminum 6061, this demonstrated a feeble joint, thus the parameters also needed to be reiterated. However, when the results for ASI 304 with PET and PC showed outstanding results, showcasing that changing the polymer material, so long as the polymer materials are consistent and their properties, their material properties are similar with each other, we can get almost strong and cohesive joints using laser welding. And with that said, I would like to thank you for your patience. That is the end of my presentation. Thank you.